here we have something called scientific notation because you use it a lot in science. It's generally this form, n times 10 to the p. This number n is between 1 and 10. This 10 to a p, p is a whole number called the magnitude. So for example, 3.2 times 10 to the negative third. This is one part in 1,000. So we rewrite it in standard notation by moving this decimal point 1, 2, 3 points to the left, 0.0032. Here's 3.2 times 10 to the third. This means this is a number in the thousands. So we move the decimal point to the right, 1, 2, 3 spots, 3,200. Here's 137,000. Now, this leading term, this n, I'm not sure what it's called, and well, it's related to something in logarithms called a mantissa, so I'm going to call it that. This part, I guess we'll call it mantissa, consists of the leading part with a decimal point just to the right of the leading digit, so 1.37. So we want to know how far to move the decimal point to get it there. Well, from here goes 1, 2, 3, 4, 5, 10 to the fifth. And here's 0.00137. Again, we move the decimal point just to the right of the leading digit to get 1.37. How far and which way do we move the point? From here we go 1, 2, 3 places to the right. So it's 10 to the negative 3. 1.37 times 10 to the negative 3. Negative exponents, negative magnitudes means numbers less than 1. Positive magnitudes means numbers much bigger than 1. So if this is negative, the thing is tiny. If it's positive, it's huge. Now, all right, these orders of magnitude, well, they go up by various names. From 10 to 99, those are in the tens. So we have a 10 to the first. From 100 to 999, that's in the hundreds. So it's something times 10 to the second. 1,999, that's in the thousands, 10 to the third. I'll skip to millions, a million to 9,999,999, that's times 10 to the sixth. 1,000, million, billion to 9.9999999 billion, that's in the billions, and 10 to the ninth. And 1,000, 1,000, 1,000, 1,000 to 9.999999999. Those are in the trillions, that's 10 to the 12th. There's also some numbers that I think really deserve to be more heard of. Between 1,000 and a million, well, you often get like tens of thousands, 10,099,999. There's a name for that. It's called a myriad. I think it's a nice word, and I think we should revive it, 10 to the fourth. And here, 100,000 to 999,999. That's hundreds of thousands, but it's also known as a multitude. These are old words, which really, like I said, I really think they should be opened up again. Whiles back, oh Lordy, just right before the first Gulf War, and there are all these people who were about to, all these people marching in the streets of San Francisco and all over the nation and the world saying, no, don't do this. There were, tens of thousands, hundreds of thousands in the streets. And for the newspaper to say myriads march or multitudes march would have had the virtue of, alliteration. But I tell you, the Chronicle disappointed me by saying thousands march. And this is on page A17. Like they were burying the lead and understating it. This disgusted me so much that I canceled my subscription. So I think these are useful words and deserve some credit. All right, now here this is. The reason why we use scientific notation like this and this, you can use it to write very small or very large numbers. And here's the thing, if you write a number like this, with all these zeros, your hand might get tired. You might, smush them into two of those zeros into each other in your haste to write. You might forget a zero, and then right away you're off by a factor of 10. In other words, wrong. Same here. You drop a 0 or 2, and you have something that's way too small. So these keep track of how many zeros, which is important given how much a 0 has effect on a number. All right. Sometimes a number is not quite in scientific notation. 23.65 times 10 to the sixth. This is not between 1 and 10. So what you do is rewrite this, 23.65, itself in scientific notation, 2.365 times 10 to the first. Then bring the 10 to the sixth over, add exponents, get 2.365 times 10 to the seventh. Or 0.0317 times 10 to the negative 2. Again, this is not between 0 and 1, so this whole number is not in scientific notation. So we rewrite this part, 0.0317 as 3.17 times 10 to the negative 2. Then bring over the other 10 to the negative 2, add the exponents. I get 3.17 times 10 to the negative 4. Now, in addition to writing very large and very tiny numbers, scientific notation also helps to divide and multiply these numbers, because the powers of 10 take care of what all the zeros are doing. 1.3 times 10 to the fourth times 7.8 times 10 to the fifth. What's that? Well, okay, we multiply the mantisses, 1.3 times 7.8. We also multiply the orders of magnitude. 10 to the fourth times 10 to the fifth is 10 to the 4 plus 5. All right, now this comes out to 10.14. This is times 10 to the ninth. This is not quite in proper scientific notation, so we rewrite this. 10.14 is 1.014 times 10 to the fifth. That times the 10 to the ninth gets you this, 1.014 times 10 to the 10th. 2.686 times 10 to the 10th over 7.9 times 10 to the negative 7. Okay, first we divide out these mantisses, 2.686 over 7.9. Here we have a ratio of powers of 10, so we subtract the powers, 10 minus negative 7. Okay, this part here comes out to be 0.34. This part comes at 10 to the 17th. Now again, this is not quite in the right form. So you write this 0.34 is 3.4 times 10 to the negative 1. That times 10 to the negative 17th, you add the powers and get 3.4 times 10 to the 16th. All right, some examples. And it's called scientific notation because in science you'll get lots of teeny numbers and lots of really large numbers, and sometimes they wind up in the same equation, and you have to be able to deal with it. So this notation follows. 9.1 times 10 to the negative fifth times 5.5 times 10 to the 12th. Okay, you have 9.1 times 5.5 here. You have 10 to the negative 5 times 10 to the 12th here. This comes out to 50.05. Negative 5 plus 12 is 7 times 10 to the 7th. Not quite the right scientific notation, so we rewrite 50.05 as 5.005 times 10 to the first. And that times 10 to the 7th, you add the exponents, and you get 5.005 times 10 to the 8th. We have 2.193 times 10 to the 32nd. My God, that's an enormous number. Over 4.3 times 10 to the 20th. Also not quite as enormous, but still ridiculously huge number. So what's the ratio? Well, 2.193 over 4.3 here. Here we take a difference of the powers, 10 to the 32 minus 20. So this comes out to 0.51 about times 10 to the 12th. And again, this is not quite right, so we rewrite this 0.51 as 5.1 times 10 to the negative 1, still times 10 to the 12th. These combine by adding, negative 1 plus 12 is 11, so 5.1 times 10 to the 11th. Now here they're just being mean. 0.000000039 times 0.00095 over 0.0195 times 4,000. Ridiculous. Okay, here we go, but we can handle this. This first number is 3.9 times, let's move the decimal point how far? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so how far to move the decimal point? Just to the right of the leading figure. Another way to count it is just to put a 0 to the left of the decimal point and then count the zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. 3.9 times 10 to the 9th. This here will be 9.5 times 10 to the negative 4. This is 1.95 times 10 to the negative 2, and this is 4 times 10 to the 3rd. All right, we gather together these mantisses. 3.9 times 9.5 all over 1.95 times 4. And here, 10 to the negative 9 times 10 to the negative 4, that's 10 to the negative 9 minus 4. 10 to the negative 2 times 10 to the third is 10 to the negative 2 plus 3. This all multiplies and divides out to 4.75. Negative 9 minus 4 is a negative 13. Negative 2 plus 3 is a 1. 10 to the negative 13 over 10 to the 1. We subtract the exponents. And we get 4.75 times 10 to the negative 14. So that's in scientific notation, and in standard notation, you write 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 zeros, 4, 7, 5. This is obviously much easier to handle. Now, if we're going to talk scientific notation, let's do some science. Light speed is about 300 million meters per second. A light year is a distance that light travels in a year. How many meters is that? Well, we'll take a year and 365.25 days per year, average year, averaging out the leap years, times 24 hours per day, times 60 minutes per hour, times 60 seconds per minute. We cancel all the units out. What's left is seconds, and it's about 31,557,600 seconds. So a year is about 31 million seconds. And by the way, a billion seconds is about 61.5 years. And this Sunday, I'm throwing a party because it'll be my second gigasecond. Anyhow, so light year will be about 300 million meters per second times about 31 million seconds. So the seconds cancel. So 3 times 10 to the 8th times 3.15576 times 10 to the 7th. Multiply it out, you get 9.46728 times 10 to the 15th meters.